Welcome to The Explainer. Today, we're diving into one of the deepest, most tantalizing ideas in all of mathematics, the Riemann hypothesis. This is all about a quest to find a secret pattern hidden inside pure chaos, a pattern that might just be the foundation for everything from our online security to the very laws of physics. So it all starts with prime numbers. You know them. They're the atoms of arithmetic, right? The indivisible building blocks for every other number. But as this quote gets at, they just seem random. You have 2, 3, 5, 7, then 11, 13, 17. There's just no obvious formula telling you what's coming next. And yet, for centuries, the greatest mathematical minds have had this nagging suspicion that the randomness is just an illusion. They feel like there's a secret order, a hidden music, guiding where the primes fall. The big question has always been, how on earth do you find a rhythm in what looks like total chaos? All right, that brings us to our first section, where we really get into this beautiful and surprisingly useful chaos of the primes. So think about it. Primes are the absolute bedrock of math, and their chaotic, unpredictable nature has been this epic puzzle for literally thousands of years. But this isn't just some abstract academic problem. In fact, their secrecy is the very thing that keeps our digital world safe. The security of your bank account, your emails, it all relies on the fact that it's insanely hard to find the huge prime numbers that are multiplied together to make even bigger numbers. So, to deal with all this chaos, you couldn't just keep staring at the number line. You needed a whole new perspective, a new kind of map. And one man, Bernhard Riemann, came up with a way to turn all that noise into a stunning new landscape, one with clear, identifiable features. You know, this quest is ancient. As we see here, way back with the Greeks, Euclid proved there's an infinite number of primes. Later, Euler started to get a sense that there was some deeper structure. But then, in 1859, this quiet German genius, Bernhard Riemann, published a paper that completely changed the game. He basically said, let's stop looking at the primes directly. Let's look at them through an entirely new mathematical universe. And the tool he created, it's called the Riemann zeta function. The best way to think about it is like a cosmic map. It's this incredible invention that takes all the information from the infinite messy list of primes and organizes it into a single, elegant structure. On this map, the chaos of the primes suddenly transforms into a landscape with mountains and valleys, all with clear, predictable features. Now, on this map, there are these super important landmarks called zeros. These are just places where the value of our function hits zero. Some of them, what we call the trivial zeros, they're easy, they're predictable, they follow a simple pattern. But the others, the non-trivial zeros, well, that's where the real mystery is. They hold the secret to everything, and that brings us right to the heart of it all, to a simple, incredibly profound, and, yeah, extremely valuable statement about where these mysterious non-trivial zeros are located. So, Riemann looks at his map, at these mysterious landmarks scattered across it, and he proposes this one, breathtakingly simple rule that he thinks governs them all. His big idea, his hypothesis, was this. Every single one of those mysterious, non-trivial zeros lies on one single, perfectly straight line. Imagine our mathematical map has coordinates, right? Just like a real map. Riemann claimed that every important landmark, every single one of these special zeros is located on one specific north-south line. This is the critical line. If you found even one zero that wasn't on it, the whole thing would come crashing down. Now, this idea isn't just elegant. It's one of the most important unsolved problems in history. It's so significant, so fundamental, that the Clay Mathematics Institute has put up a $1 million prize for anyone who can deliver a correct proof. Okay, so why? Why does one little line on a mathematical map matter so much? What's the big deal? What does proving this hypothesis actually unlock for us? Well, if it's true, first off, it would totally crack the code of the primes. We'd have a precise map for their distribution. Second, it could have huge implications for cryptography, though people actually debate whether it would make it stronger or weaker. Third, and this is where it gets really wild, the spacing of these zeros seems to perfectly match the energy levels in quantum physics. Nobody knows why. And finally, all of this points to a deep, profound cosmic order, suggesting that the rules of numbers and the rules of the universe might be one and the same. So you gotta ask, have we checked? Oh yeah, we've checked. As you can see, the progress has been just explosive. Today, supercomputers have verified not just billions, but over 10 trillion of these non-trivial zeros. And get this, every single one falls perfectly on Riemann's critical line. Not one has been found out of place. But here's the catch, and it's a huge one. In mathematics, checking 10 trillion examples or even 10 trillion trillion is not a proof. A proof has to work for all of them, all the way out to infinity. There's always that tiny, nagging chance that the very next zero we find, or one a Googleplex away, will be the one that veers off the line. So that leaves us in this incredible state of suspense, which gets to the real soul, the philosophical heart of this whole unending quest. We're really looking at two amazing possibilities here. If it's proven true, it'll be a triumph for humanity, a moment where we pull back the curtain on the universe's fundamental rules. But if it stays unsolved or is even proven false, well, that serves as this beautiful, humbling reminder of our own limits and the enduring power of a great mystery. And that really gets to a crucial point. The chase itself has been unbelievably fruitful. The quest for a proof, even without an answer, has created entire new fields of mathematics. It's really a story about human passion, creativity, and our relentless, unstoppable drive to understand. So in the end, we're left with this powerful, provocative thought. The Riemann hypothesis is way more than just a math problem. It's a search for the universe's hidden music. And it makes us ask a really fundamental question. Is the goal to finally hear the complete song? Or is the real masterpiece found in the very act of listening for it?